Welcome to another GIA Knowledge Session. This is a series of talks and seminars about gemology, fueled by our decades of research. Today, I'm your host, Evan Smith, filling in for our normal host, Kelly Giordano. And a thing that comes up often in conversations about diamonds is this idea of diamond ages. Diamonds are almost as old as the Earth itself, billions or millions of years old. And I think that's a fascinating question. But how do we actually get to the bottom of that kind of a question? Well, today we've actually got two excellent speakers who can speak to this perfectly. We're joined by Dr. Karen Smit, GIA Research Scientist, and Dr. Stephen Shirey, Senior Staff Scientist at Carnegie Earth and Planets Lab in Washington, D.C. And these are not only knowledgeable people about this topic, but both of them have put in many, many painstaking hours to do the work necessary to make some of these age determinations. So this is the absolute perfect duo to tell us about it. Now, before we get started, a bit of housekeeping. Everyone attending this meeting is automatically muted. But if you have a question, please do submit it using the Q&A feature that you'll see at the bottom of the screen. Feel free to ask questions as we go, and there'll be a Q&A session at the end. We'll also send a recording of the session to you later today, and that message will have a survey where we'd love to hear your feedback about this discussion today. And with that, I'd like to turn it over to you, Dr. Karen Smit.
Thank you very much, Evan. So thank you very much for the introduction. So as Evan mentioned, I work at GIA here in New York City. I'm a research scientist. My background is in diamond geology. So I have a master's and a PhD in diamond geology. And I received my PhD from the University of Alberta in Canada, same as where Evan is from, in 2013. I've been at GIA here in New York since 2014, so 6.5 years here in New York City. So today we're joined by a very special guest, Dr. Steve Shirey. He's been a frequent collaborator of both Evan and I. Steve and I have worked together for 13 years. He was the first person who introduced me to isotope work in the Clean Lab, and we're going to be talking a bit about that today. So thank you very much, Steve, for taking the time and for joining us today. So maybe if you can start just by telling us a little bit about yourself before we get started with the talk.
Well, it's a real pleasure to join the GIA fold today. I've been a collaborator with Evan and Karen, as she mentioned, for a number of years, and it's been a great partnership and teamwork. I became interested in diamonds probably 20, 25 years ago when I thought about the idea of using them to probe the deep geology of Earth's continents. And with postdoc Graham Pearson, he and I developed a dating technique that we used, and we'll talk a lot about today, to try to relate the timing of diamond growth to the deep geology of the Earth's continents. And we're now using it to look at the deep continent, the deep mantle of the Earth, and how plate tectonics play a role in producing fluids that get down into the diamond forming region. I got my PhD at the State University of New York at Stony Brook, where I learned a lot about Archean geochemistry and was a dyed-in-the-wool field geologist and isotope geochemist, and was only introduced to the micro world of diamonds late in my career. But as I like to tell people, if you were to send a rover to another planet and were able to obtain a specimen that was from 400 kilometers or 700 kilometers or 150 kilometers from beneath the crust of that planet, it would be the most precious sample you could use to unravel the geology. So that's what we hope to try to talk about today.
Okay, well, thank you very much, Steve. So today we're going to be talking, as you can see, about diamond ages. We'll explain a bit about the process behind obtaining the diamond age. So we spoke, Evan mentioned that, this is a lot of painstaking work in the lab. So we'll talk a little bit through what that process entails. And of course, like the big question, are diamonds really forever? Spoiler alert, no, they're not. So towards the end, we'll talk a little bit about some of the processes that can destroy diamonds. But we'll talk about how old the oldest diamonds are and where they're from. We'll also talk about, we often get questions, are diamonds still forming right now? And also, show a few examples where, diamonds from a particular mine aren't all necessarily the same age. And then Steve's going to cover some topics, just sort of explaining why diamond ages are actually important. Beyond knowing how old they are, why do we actually care beyond that about these diamond ages? So we all know from popular culture, diamonds are forever. We've all heard the slogan. We've hopefully seen the movies and heard the songs. It's a pretty powerful slogan. That De Beers introduced for their advertising campaigns back in the 1940s. So here's just a few examples of some of the advertising that Forever Mark is using. Like forever has no end, but it does have a beginning. And so that's, I guess, what we're hoping to sort of show you today is, what is the beginning? When did diamonds actually form? So before we get into the ages, I guess we just want to cover, just a few basics, like, well, where do diamonds actually form? Where in the earth do they come from? So here's a cross section of the earth here on the left. It's centered on Africa because Africa happens to be the most important continent. That's where I'm from, South Africa, if you haven't been able to place my accent. The Earth's cross section, so we have the crust, which we're on. The crust is just this very little thin skin all the way on the outside, and then it's the mantle, and then the core, which is the outer core and the inner core. So the majority of the diamonds that we see at the surface today comes from the mantle. So we've sort of blown up the mantle portion of this cross section on this figure here, here on the right-hand side. So the majority of the diamonds that we see on the surface or that we wear in our jewelry comes from this region in the Tectonic lithosphere. So cratons are the oldest portions of the Earth's crust that have been stable for billions of years. The reason that these cratons, these old portions of Earth's crust has this long-term stability is because they have this keel or this root that stabilizes it and sort of protects it from being heated up and destroyed. So the majority of the diamonds that we study and that we see today are from the lithospheric mantle below these cratons, below the ancient continents. Hopefully people are familiar with Evan's work. He's done some pretty spectacular work on deep, rare, super large diamonds. And these come from much deeper than these lithospheric diamonds. They come from an area known as the transition zone and the lower mantle. So we have the blue diamonds and clipper diamonds forming in the transition zone and the lower mantle. But by far the majority of the diamonds, and certainly all the diamonds that have been dated thus far, come from this region called the Tectonic lithosphere. So if diamonds are forming at these great depths deep in the earth, how do we actually have diamonds at the Earth's surface today? The reason for that is kimberlite eruptions. So kimberlites are a type of volcanic eruption that originate from great depths within the Earth. So they come from around 200 kilometers beneath the Earth's surface. They're incredibly explosive, much more explosive than the volcanoes that we see today. And they're thought to reach the surface in a matter of hours or potentially up to a day or two. The last diamond-bearing eruption that became sort of a diamond mine occurred 20 million years ago. So this was the Ellendale eruptions in Australia. So these aren't typical volcanic eruptions. The point we want to make here is that these are rare, explosive eruptions that are completely different to the types of volcanoes that we see today, for example, Hawaii or Iceland or Cascadia. So these are much more explosive and they're incredibly rare, but they come from great depths. And so on their way up to the surface, because they're so explosive, they can bring materials to the surface with them. So they bring xenoliths and diamonds to the surface with them. And so what we do know is that diamonds are crystallizing at great depths from carbon-bearing fluids and melts. Geochemists or diamond geologists are still debating or figuring out the exact details about how diamonds actually are forming. But regardless of the details that we debate, we do know that they're forming from fluids and melts in the deep earth. And so that is why geologists want to study natural diamonds. We want to study the inclusions in them, and we also want to study the diamonds themselves, because they can tell us so much about what processes are happening deep in the earth in a way that we can't get from any other samples. Diamonds are coming from much, much deeper than any other gemstone. So most other gemstones are coming from the crust, whereas diamonds are coming from much deeper. And so these are samples that can inform us about the very deepest processes that are happening in the earth today. So I'm going to hand over to Steve here, and he's going to talk to us a little bit about why we can't date diamonds directly.
All right, thanks, Karen. So a big problem in dating any mineral is whether you can date it, the crystal that you actually have. And with diamonds, we have a problem. If you can go to the next slide, please. We have a very pure structure, and we have almost nothing in the diamond except nitrogen. So we're very, very free of materials or atoms that are radioactive that will decay to use geochronology as a tool. So here's on the left, the structure of diamond and the structure of graphite. And in both cases, you have quite pure native forms of elemental carbon with almost nothing that's available to do the dating with. Next slide, please. So here's the problem with carbon dating. We have a lump of graphite here that says that you look older than your profile picture, and the diamond on the right says she's been under a lot of pressure lately. So one of the questions we get that's fairly straightforward is, well, if the diamond is carbon, 100% carbon, why can't we use carbon dating? Because people hear of carbon dating, they know that carbon dating is a very common tool, and it's a very simple reason. Carbon-14, which is the radioactive atom of carbon that will decay to nitrogen, is a very short-lived radionuclide. It decays very fast. Furthermore, it's formed in the atmosphere by spallation reactions and is not really in equilibrium or in communication with the diamonds, which are deep in the mantle. So we have two problems. One is we have almost no decay product to date because it's a very fast-lived decay, and we also have no carbon-14 that we can get from the atmosphere into the diamond. So carbon-14 is just completely not a possibility to use to date diamonds. We go to the next slide, yes. So we use other radiogenic decay systems. And what are these systems? Well, they're based on long-lived radioactive decays of different trace elements. And these trace elements are found in minerals that are included in the diamond. They're not in the diamond lattice itself. And Karen will get into some of these minerals in a little bit. But just to compare the dating that we're going to be doing with this carbon dating example I showed earlier, what we have is an hourglass. The top of the hourglass is the parent isotope, and the bottom of the hourglass is the daughter. And the neck of the hourglass would represent the decay constant, or the rate at which decay would happen between the parent isotope and the daughter isotope. And so it's in principle quite simple. If we can isolate the parent and the daughter, and we can measure precisely the daughter accumulated radioisotope, like 143 neodymium, 187 osmium, or 87 strontium, like you see on the lower right of this slide here, then we can, in principle, knowing the decay constant and the accumulation rate, we can calculate the age, and we'll show you how this is done. And the important reason that we use this type of decay scheme for dating is that when we're dating old minerals, the older the mineral is, the more accumulation of the daughter product that is, so that the easier it is to measure the age if you don't have very much of that particular radioactively derived element occurring in the mineral inclusion. Okay, next slide, please. Right, so what we're going to do is we're going to talk about how the diamond acts like an hourglass by trapping a mineral inclusion in it, which will be like a clock, where the parent radionuclide is going to decay to the daughter radionuclide. And if we can get the mineral out without compromising, in other words, by compromising, I mean losing the parent and losing some of the daughter, in the chemical procedure to isolate these elements, then we can actually measure the age of the diamond, assuming that the diamond enclosed the mineral at the same time. The mineral grew and was closed system at the same time that the diamond incorporated it. Karen, you want to talk a little bit about the type of minerals we use to date diamonds?
Yeah, so in the next few slides, we have a few examples just of what these minerals actually are that we can use. You know, minerals that are trapped during diamond growth. So these are minerals from the deep earth, and because they're trapped in the diamond, they're actually pristine samples of the deep earth, you know, without alteration that we can study. And so a lot of the dating work has been done by our colleague Steve Richardson. So he's over here, up here on the left. And so the first study that determined the age of diamonds was this landmark study by Steve and others in Nature in 1984. And this was done using garnet inclusions in diamonds. So they did garnet dating using samarium, neodymium, and rubidium strontium systems. And importantly for these very early studies, several hundred inclusions needed to be composited or grouped together in order to get sufficient concentrations of these radiogenic elements so that you could get a signal on the mass spectrometer and actually measure that. And so, you know, the other person that we've highlighted here is John Gurney. So actually Steve and John were both my master's advisors at the University of Cape Town. And so, you know, they gave me my start along with Steve Shirey. They gave me my start in the diamond world. And so Steve just has a little anecdote that he wants to share about Steve.
Well, this is really more for the students in the audience and younger people. I met Steve Richardson in 1979 when I was a young technician at MIT in Cambridge, and he had just started this PhD work that we're seeing Karen display here in this Nature paper, this publication. And I had no idea what he was doing with the diamonds. I didn't know anything about a diamond. I didn't know you could determine the age. No one did at the time he did the work. And but we just knew each other casually. And I went off to do my PhD at Stony Brook, left MIT, and 4 years later submitted a paper at exactly the same time Steve Richardson did. So this paper of Steve's and my very first paper in Nature were back to back in the same issue of Nature. And then we subsequently, 10 years later, got together to do a lot of collaborative work in dating diamonds that he wanted to use the technique we had advanced, sulfides, which Karen will talk about. And so the point here is that you never know when you bump into someone early in your life how many times you're going to run up, you know, across the path. And it was a great, it's been a 40-year collaboration for Steve and me, and really quite a bit of fun.
Yeah, so you'll see Steve Richardson's name come up a lot during this talk because he's determined diamond ages from, you know, a number of localities worldwide, but we just sort of wanted to show, you know, what he looks like, so you can see that, you know, there's a person behind all this data that you're seeing. And so, you know, with improvements to analytical sensitivity in the last few years, single inclusions can now be measured to obtain ages. So I mentioned that, you know, in this early work, what Steve had to do was he had to composite a bunch of inclusions, like several hundred inclusions together in order to get, you know, sufficient concentrations of elements on the mass spectrometer. However, now we have improvements to analytical sensitivity, and this is being sort of led, this effort is being led by Gareth Davies in Amsterdam. He's here in the middle with Ingrid Chin from De Beers and Suzette Timmerman, who did her master's with Gareth. And she was the person who produced the first results for this new technique. So using the single inclusions on these silicate, single inclusions on silicates in order to obtain diamond ages. So, you know, these inclusions are very, very colorful, very beautiful inclusions, but they're actually also very useful because they can tell us something about the deep earth. So sulfides are less visually appealing to some. They're not as colorful. However, they're my favorite mineral because these are the inclusions that I've been working on to determine the ages. So sulfides, you know, have this more silvery gray appearance when they're still enclosed in the diamond. And they always have these fracture systems around them, these fractures that are filled with graphite and maybe some sulfide that's smearing sort of into the fracture systems. But it's analyses of these inclusions as well that allows us to determine the age of the diamond, just using, you know, a different isotope system. In this case, we're using rhenium-osmium. And so the first ages that were determined from sulfide inclusions, once again, Steve Shirey collaborating with Graham Pearson here. So Graham was one of my PhD advisors. And so Steve and Graham worked together to develop the rhenium-osmium system to be applied to single inclusions in diamonds. And since this landmark study in 1998, it has become one of the most widely used systems to date diamonds. And so once again, Steve just has a little anecdote that he'd like to share about Graham.
Yeah, so this again is for students in the audience, but Graham appeared in our lab one summer. He was building his lab at Durham and didn't have any equipment yet. And he showed up with a 3x5 card that Jeff Harris, who's the third author on this paper, had given him, where he had taken some diamonds and cracked them open. Karen will show how that works in subsequent slides. And he'd taken these sulfides out and put them on a piece of Scotch tape and then taped them to this 3x5 card. So Graham shows up in the lab with about 8 little pieces of Scotch tape with little numbers labeled on them. And it looks like just little pieces of dust on your desk, you know, I mean, very unimpressive. And Graham says, hey, I've got these sulfides. We should just try to do osmium on them. And I'm looking at Graham and said, you are out of your mind. This is not going to work. And so the first point I want to make is that if your advisor ever tells you that something is not going to work, don't listen to them. And so what we did is we went ahead and we started to figure out how we could get this system to work where we could analyze small sulfides. And one thing led to another. We spent the whole summer working on this project with our colleague Rick Carlson, who also was heavily involved in making sure the mass spectrometer was sensitive enough to do the work. And by the end of the summer, we had some results. And so you know, the other part of my point is that you really need to persist in life and simply just give it a shot. So this work was so successful that John Gurney recommended Graham Pearson for the honored Waldemar Lindgren Award of the Society of Economic Geologists, and Graham won the Waldemar Lindgren Prize of the Society of Economic Geologists for the ability to date diamonds for this work. So that's really the, you know, it doesn't always work out like that, but when it does, it's quite amazing. Back to you, Karen.
Yeah, no, thank you. Yeah, so it's a great anecdote just to sort of share how important this work became, because even though they had to, you know, develop a new technique in order to date diamonds, since that time, it's become the most widely used technique to determine ages for diamonds. Okay, so I guess the reason everyone is here is to actually find out how old diamonds really are. So here's, you know, we've got a timeline here, and we've just sort of given a few key ages. So I'll just sort of give a snapshot of a few of the ages, and then after that, Steve's going to go into a little bit more detail about different mines and their different ages. So we have the age of the Earth, which is 4.56 billion years old. The oldest rocks, both of these localities, Nouveau-Argatouk and Acasta, are in Canada. So, you know, Canada has some of the oldest, or it has the oldest rocks on Earth that we know of, comes from Canada. The one is in the Northwest Territories, and the other one is in northern Quebec. But certainly, I mean, these rocks are over 4 billion years old. The oldest diamonds that have been dated thus far are from Ekati and Diavik. So these diamonds are 3.5 to 3.3 billion years old. And what I find impressive about those ages is that it shows that diamonds were forming even before our atmosphere had any oxygen in it. So before life really blossomed on Earth, diamonds were already forming deep in the Earth's mantle. So we also have a few other examples here from Kimberley in South Africa, 2.9 billion years old. The Cullinan and Venetia diamonds, some of them are 2 billion years old. However, you know, not all diamonds are that old. We also have diamonds that are significantly younger. So what geologists call young would be like 90 to 60 million years ago. So those are the youngest diamonds that we know of, are diamonds from Jagersfontein and Koffiefontein in South Africa. They are 90 to 60 million years old. And so even the youngest diamonds that we know formed prior to the dinosaurs going extinct 65 million years ago. So yes, diamonds are forever in terms of millions to billions of years old. However, not all diamonds are billions of years old. Geologists like to say, oh yeah, these are super young diamonds, they formed just the other day. But in terms of human lifespan, and if you place it in terms of the dinosaurs and our Earth's evolution, that actually is, that is a long time ago. And so other key localities that we've pointed out here is, some of the Argyle diamonds we know formed at 1.6, the Ellendale diamonds at 1.4, and the Victor diamonds, also from Canada, formed 720 million years ago. And so passing back to Steve.
Thank you, Karen. So this is the, title page of a paper that was published this fall in Geochemica et Cosmochemica Acta, a geochemistry journal, research journal. And Dan Howell is the first author in this particular paper, but Karen and I are both co-authors. And what this paper does is look at all the dated diamonds that exist in the world and their carbon isotopic composition. And the idea was to sort of see what the carbon isotopic composition variability is with time. We're not going to talk about that so much today because we're talking about diamond ages. The carbon story is a whole nother story, which we can talk about in the Q&A if people are interested. But on this plot here that Dan made from this paper, we have a variety of diamonds. Notice on the left we have the time scale. So GA is giga-annum, that's billion years, so 4 billion down to 0. So your older diamonds are up at the top. We have the localities labeled here: Panda, Diavik, Udashnaya. These are famous mines that many of you will have heard of from articles in Gems and Gemology, or just knowing where some of the diamonds you've sold have come from. And pay attention to the shape of the points here. We've got squares which represent what are called pritatitic or Hartsbrigitic diamonds. These are diamonds that look like they have mantle inclusions, and they look like they're coming from incorporating minerals that are more like the mantle than the crust. Whereas the ones that have the diamond symbols are eclogitic diamonds. We call eclogitic diamonds. These are ones that look like they incorporate basaltic type mineralogies. And the point to make with this particular slide is that diamonds are forming for a long time in Earth history, as Karen just showed, from 3.5 billion all the way down to very, very young diamonds down at the bottom here. And we'll talk about how this shows up in different mines because it's pretty interesting. Okay, next slide, Karen, please. So if you look at the Akkadian Diavik localities, a lot of people know about this particular set of mines in the Slave Craton of Canada. These are the two most prolific diamond producers and really responsible for the Canadian diamond rush, which took place over the last 20 years and is well documented in the book Barren Lands, which is a great read if anybody wants to learn about how the diamonds were found. But if you notice in the circles on the left, Panda is the same as Akkadi. Okay, so Reed Panda and Akkadi is the same, and Diavik, of course, is distinguished there. What you see is the oldest diamonds at around 3.5 billion in these localities. But then there's a second generation of diamonds forming at Diavik in particular at 2 billion, and very, very young diamonds down at the bottom there, mostly fibrous. If you see their circles, so these are fibrous overcoats that are grown on top of monocrystalline cores. You would never see these in the jewelry trade, but they would appear in the rough, and you could make jewelry out of the monocrystal. You can see that in this one diamond mine, you have 3 different generations of diamond formation that span 3.5 billion years. And so Steve Richardson, in his age dating, was one of the first to notice this, but it's an important feature of diamond mines that you might have multiple generations of diamond formation that show up brought to the surface by the kimberlite. Next slide, Karen. A really good example of this is the famous mine Premier or the Cullinan mine, the premier kimberlite, which is 1,200 million years old. And it has some super deep diamonds that are blue, the kind that Evan's worked on recently, and shows that they might be some of the deepest diamonds that have ever been found. And so what we see here at the Cullinan mine is, again, 3 generations of diamonds, starting with Hertzbergitic, their oldest, a mixed laerzolitic, which is mantle-like, and eclogitic, that are, again, about 2 billion, and then a younger generation at about 1 billion. The importance of these oldest blue diamonds is that if the blue diamonds are formed as some of the deepest ones from slabs that have brought altered serpentinite materials down, like Evan's work has shown, then this could be the first onset of this kind of very, very deep subduction process. We'll talk a little bit more about how we can make big inferences about mantle convection from diamond ages, which is one of the key features of why we want to know the ages in general. Finally, we look at Argyle here, and people are very, very familiar with Argyle because of its huge diamond production and also the long history of production of pink diamonds here, and the fact that Argyle is closing this year. And Argyle diamonds, they don't seem to have quite the same range of different generations here, but an age around 1.6 billion. And so you can see that every diamond mine is a little different, and some include age ranges, and some include just single ages. So back to you, Karen. Let's talk about the process to do the dating in the lab.
We've now shown you sort of like the range of ages that you can expect for diamonds, showing that they span all through Earth's history. But to actually get these data points, actually, it's a significant amount of work. These aren't routine analyses. You don't just get a diamond, date it the same day, and then have your result. This is meticulous work that often takes months to do. And so, there's a few, different steps, and it is a destructive technique. So it does involve destroying the diamond. And so really, if you have a diamond in your hand, you don't know how old it is, because to date a diamond is a destructive process. And, we start off by laser cutting and preparing a plate. So we just want a double-sided surface on the diamond so that we can see nicely into the inclusions, and so we can plan exactly what we're going to do. We also want to see what inclusions we're sort of dealing with, if there's multiple inclusions or single inclusions. And that's often easier to see if you have a nice double-sided plate rather than a whole diamond. And so we just we mount them, in a gadget like this for the laser cutting. We want the diamond in a very particular orientation for the cutting. And then we also obviously want to preserve the inclusions, sort of within the double-sided plate. That plate, after we sort of characterize it by different techniques, once we've characterized the diamond plate, we now want to obviously, break the plate and get the inclusion out. So we have this diamond cracker, very specialized technique, put the diamond in and hit it with a hammer. It's very high tech. And so I guess that's your first hint, diamonds are not forever. They can be destroyed very easily with a hammer. So we put the plate across, these tungsten bits, which are also very hard. We place the diamond plate, across those tungsten bits, place it in the cracker, and then, break the inclusion out. And so the inclusion is actually here, right there in the middle. It's that tiny thing there. We've actually circled it just in case if you don't believe us, there's something on that piece of black carbon tape. So these inclusions are always, very small. And so it's a lot of detailed, meticulous patient work, because you need to, transfer the sulfide a few different times using a tweezer and not lose it, in the, I think 5 or 6 times that you have to transfer it during, all the steps that you do sort of in the lab. And so, the reason that we place it on the carbon tape is because we want to characterize it for later. But, before we get to that, I just wanted to show, before we show the electron microscope pictures, I just wanted to show the optical microscope pictures to show sort of what these sulfides actually look like. And so this is a 500 micron scale bar. You can see that, the tiny sulfide there. And then on the right, I think the scale wasn't calibrated that day, so it doesn't have scale bar, but I remember it was like 90 to 100 times optical magnification. So this is sort of the maximum magnification that you can get on an optical microscope. And this, that is sort of the size of the sulfide that you can see. And that is why we want to use an electron microscope so we can really see the sulfide and also understand its composition. And so when you put it in an electron microscope, which is just a very specialized tool that you can use to image submicroscopic grains, we can see the very nice morphologies on these sulfide inclusions. You can actually see very nice cubo-octahedral morphologies, very similar to a diamond shape on the sulfide inclusion. And then we just want to understand what the composition of the sulfide is. And in particular, you know, we're interested in the nickel composition because we need that information for later on during chemistry. We need to know what the nickel content is. So, you know, after we've characterized the sulfide grain and learned as much as we can about it, we dissolve that grain in order to do some chemistry and separate out the different elements that we want to analyze. So we dissolve the grain, we do chemistry procedures in the lab and separate out the rhenium from the osmium. So rhenium is the parent and osmium is the daughter. So it's rhenium-187 decays to osmium-187. And then those are the two that we are interested in order to determine the age for this inclusion in the diamond. So once we've done a whole bunch of steps in the lab, so we're skipping over like a lot of the steps here, you know, we end up with our osmium in this tiny little drop over here. And we place that on a filament, and we place these filaments in an instrument called a mass spectrometer. And this drop is actually dried prior to us putting it in the instrument. I guess I should say that, because that drop's not going to stay in that place when we turn it upside down. So, you know, we place the acid with the osmium in it on this small filament, we dry that down, and then we put it in the instrument, we slowly heat the filament up so that we can ionize the osmium and measure its isotopes. So just to sort of conclude this section, we just want to say, you know, this is a lot of meticulous work. This is often months in the clean lab that, you know, you spend doing your chemistry. And before that, you know, laser cutting and polishing your diamonds, and then, you know, breaking out the inclusions, not losing them, and, you know, transferring them a few times. And so this is a lot of meticulous patient work. And often this is done by PhD students who can have, you know, a few months or a few years, and they can take the time to do the work. Or it's done by researchers who can take sabbaticals. So I know, you know, like Steve Richardson often goes to Carnegie on sabbatical for a few months, and then he has time to spend doing this very meticulous work. And so, you know, often this work is, you know, because it's done at universities, it's, you know, it's done in labs that are set up for this type of work. Because these aren't sort of routine analysis, you have to go to labs that have been, like clean lab that has been set up for the specific technique. And so there's only, you know, I think 2 or 3 labs in the world that can do this type of work. And so, you know, and often, you know, to have these labs up and running all the time requires a lot of funding. And so, you know, like in Amsterdam, where they're doing a lot of the silicate dating work, you know, they receive funding from funding organizations such as the European Geosciences Union. In Canada, they're receiving funding from NSERC. And here in the US, a lot of the diamond work is also funded by the NSF. And so, you know, this is a lot of meticulous work where we need established labs. And so it's, you know, it's not routine work, but, you know, when we do get the results that we wanted, you know, it's very rewarding. So, and now Steve is going to talk to us about how to calculate an age once we've sort of obtained the isotopic compositions in the mass spec.
So an important part of the diamond work is knowing how the diamonds relate to each other. And they come up in the kimberlite as xenocrysts. And by definition, they're carried and mixed up and jumbled up by the volcanic eruption. And so we don't really know when we start the analysis if we're going to have one age from a set of diamonds or 2 ages or a jumble of things. Karen, can you go to the next slide, please? And so what we try to do is we try to pick diamonds that look like they're part of a similar group of diamonds that have the same kind of characteristics, the same kind of inclusions. So if we have, let's say, pyrititic inclusions, sulfides that have very, very high nickel, or eclogitic inclusions, sulfides that have very, very, very low nickel, we try to group them together because it's more likely that they're formed from the same kind of geologic environment and the same kind of geologic event, and we'll be lucky when we collect them at the surface to have them relate to to each other. So when we have that happen, what we do is we mathematically calculate the age, and I'm showing you the graphical representation of that mathematical calculation. So if you look on the right-hand part of the slide, you'll see light gray symbols that represent different diamonds with different inclusions, and each circle is an inclusion. And you can see that the position on that diagram has different amounts of the parent isotope. So those inclusions with the higher amount of the parent isotope will decay to higher amounts of the daughter isotope, and shown in the dark black symbol there. And the amount of decay that happens will be a direct proportion of the amount that you start with and the amount of time you have. And so in the end, the math gives you a slope to the line, which can be directly related to the age. And so we use this sloping line called an isochron diagram to do two things. We use the slope of it to give us the age. We also use the adherence of the symbol of the points on the line to kind of see how related the diamonds are. So if we look at the left-hand slide, here's a figure from a paper that Steve and I and others published in 2001, I believe, if I remember correctly. And on the bottom, we have the parent-daughter ratio, the 187 rhenium to 188 osmium ratio. And on the left, we've got the 187, the daughter radionuclide ratio to the stable 188 osmium. And the slope of this line that you see drawn there is a 2.9 billion year slope, so 2.9 GA age. What this tells us is that these diamonds, there's like about 12 of them on this line, make a pretty good agreement to the same age, and probably tell us that in the mantle, 180 kilometers down, when the kimberlite picked it up, we had a diamond growth event that incorporated all these sulfides at the same time. Now, if we didn't get such a line, we would conclude that maybe we had a problem in the analysis. Okay, that's always a possibility. Or we could conclude that there's so many different diamond forming events and so many fluids pervading that we can't really tell the age. But in this case, we got a very good result, and no one doubts that in this region of the mantle, under the Kimberley area, the very first diamonds to be systematically mined in South Africa, these are 3 billion year old diamonds that are forming. Okay, next slide, please. Work that Karen did with the GIA during her fellowship postdoc there on the Zimi locality in West Africa is shown in this slide, and we have the same diagram on the right that gives us this geographical representation of how decay occurs and how we can calculate the age from the slope. On the left, we see much more shallowly sloped lines, just so we can display them correctly. And what's interesting is she has displaying diamonds that have more than one inclusion in them. So it's a Zimi 07 there, the open symbol, had 3 inclusions. Zimi 08, the light gray, had 3 inclusions. And Zimi 09, the black square, had 4. And again, these are hard analyses, and so we have uncertainties in the analyses, and this is also natural geology for which there's variability. But what you see here is 3 very parallel lines that have the same 650 million year slope. And this is kind of the gold standard in age determination in mineralogy. Is if you can get one mineral with 3 different chronometers, it's like we have 3 hourglasses in this one diamond, and they all give us, in the 3 diamonds, they give us the same age. And so this is what we call a mineral isochron. And what they show us is that again, there's a 650 million year old diamond forming event in this area of West Africa. So let me just then break a little bit and talk a little bit about what diamond ages have taught us. And this is the part that I get the most joy out of, because it allows us to relate an age, which is really interesting, to some serious geology on the scale of a continent or part of a continent. So on the left here, I show a figure from the Gems and Gemology paper that Jim Shigley wrote with Russell Shore and others in 2016. The pink pattern you see that looks like a teardrop are the old rocks in the slave craton that Karen was talking about earlier. And if you show Diavik and Akkadi there in the middle, Karen, that would be great. So the Akkadi and Diavik mines are right there in the middle of the craton. Most of you, I don't think, are geologists, and so it's not really important to pay much attention to the colors on this map, but simply to show that the large-scale pattern that one can see in relating the assembly of a piece of crust like this can be related to the diamond ages in a way that tells us information that's not available or obtainable other ways. So we look at the right-hand panel, which is a figure from a paper by Herb Helmstedt, who by the way, was Evan's master's thesis advisor at Queen's. This cross-section illustrates how the diamond ages in the slave craton fit and force us to think about the deep structure of the craton in a way that we would not know about without the diamond ages. So what's very prominent here is a purple center part of the craton. This part of the craton has the oldest rocks and it also has some of the oldest diamonds, around 3.5 billion. Below that is another suite of diamonds. Remember in the picture I showed from the Dan Howell paper at Diavik, we had a 2 billion age a group of diamonds. Those 2 billion age group of diamonds are related to a slab which was underthrust from the west underneath this older part of the craton. And so this is the kind of thing that we, in a big sense, we try to take the diamond ages to tell us about. So if we go to the next slide, please. So some of the things that the diamonds have told us are how the mantle root beneath the continents form, how the mantle root might be modified during mountain building. Now remember, this is a look at these processes at 200-kilometer depths or something like that in the continent, which is inaccessible any other way. Important for the diamond community and for the exploration community is where the diamond fluids come from and how they get there. What were the geologic processes that brought these diamond forming fluids deep into the lithosphere? And if we can figure out how they got there, maybe we can find a better way to look at where they are and find it would help with diamond exploration. We know that Earth is a plate tectonically active planet, and so a very important thing that diamonds have taught us is the role of plate tectonics in recycling these superficial components, because many of these diamonds look like they have a surface connection, and as we get wet slabs that are impregnated with seawater, subducted by plate tectonics, the diamonds help us understand the nature of that process and the timing. And we'll talk about the last two, kind of how continents are constructed and maybe when plate tectonics started as a process that we recognize that looks something like today's process. So in this next slide here, this is a little bit like what I talked about for the slave craton. If we look at the right-hand panel, we see a very crude sketch map of the Kopval craton, Karen's favorite place on Earth. And if you look at the pattern of solid black diamonds versus open white diamonds, what you see is that all the solid black diamonds, which are mines that have a preponderant 2.9 billion year old group of diamonds, all of those sit on the west of a suture zone between two halves of the craton called the Colesberg lineament. To the east of that, where the white diamonds are, we have no 2.9 billion year old diamonds. And so the question arises, how does the craton get put together? And if you look at the left panel, what you see is a very crude diagram of the two blocks of the craton, the Kimberley block on the west and the Witwatersrand block on the east. And you see an underthrust slab, which became carried sulfur and volatiles that became diamond forming fluids, which then was underthrust to the west and allowed these fluids to rise up into the lithospheric mantle. And just from the age pattern of the diamonds, this has to be the way that diamond forming fluids got into the lithosphere. They couldn't have got into the lithosphere with some other pattern or some other basis. So let's talk a little bit about plate tectonics. So plate tectonics is on the left. This is the slide that Karen showed you earlier of the modern Earth and deep diving plates. And what's very interesting, I've highlighted on the right all the diamond ages that we have data for that have been done. And everything inside the red pattern are eclogitic diamonds, that the type of diamonds that have affinities to basaltic materials that are part of subducting slabs. And what you see is that these materials these type of diamonds appear at around 3 billion years in Earth history. And so it's very so what this tells us is that we have perhaps slab subduction of diamond forming fluids like what we see on the left, that we don't see evidence really in much detail for before about 3 billion years. And right now, the geological community is deciding whether this deep evidence for slab subduction is directly related to the surface geology that tells us that plate tectonics might be starting a little bit earlier or might be starting around this time. This is an active debate in earth science right now as to when did plate tectonics start, because there's an earlier form of recycling and heat release. It's not plate tectonics, and knowing how the Earth made its transition from that type of geodynamics to the current system is a very, very important planetary feature in just understanding the Earth and how it forms. So now we're going to turn to a less favorite part of the talk from my perspective, but one that's also very interesting. Can diamonds be destroyed? Are they not forever? Karen?
They are not. Diamonds are not forever. I wrote it on a colleague's whiteboard this morning, just so that he can remember that diamonds are in fact not forever. So yes, diamonds can be destroyed. We've already, sort of spoken about how, you can, break a diamond with a hammer. And I think most people are familiar, with, like in their jewelry, they want to be careful so that the diamond doesn't get any chips. And so yes, diamonds can be destroyed. And so here's a very nice example of a diamond octahedron that has been cleaved along its 111 plane. So I'm hoping that many diamond dealers and jewelers will be familiar, with the 4 sort of cleavage directions in a diamond. So along sort of the 111 crystallographic plane. And so I've sort of shown the idealized sketch of an octahedron on the left. You can sort of compare the shape of this diamond. It's sort of maybe like half or a quarter of what it once was, because it's been sort of cleaved along that 111 plane. And, this obviously happened in nature. This is an alluvial diamond, so it's already, sort of in a river environment. And so we don't know when this diamond broke. It may have been in the kimberlite on the way up to the surface. Maybe it was smashing around a bit. Maybe, in brittle deformation deep in the earth, maybe some sort of earthquake mechanism. Or potentially just, in the fluvial river environment, it was sort of banging around with other diamonds and then broke. So, there's a number of different mechanisms through which, diamonds can break sort of naturally, just through natural processes that are happening. But I wonder how big this diamond was, sort of originally. Because it's already a pretty large diamond. And then if you think, what the original octahedron looked like, it must have been massive. I guess, sort of the most common form of, sort of diamond destruction or diamond dissolution is, just through fluid resorption. And so this is an extremely common process that is happening both, in the earth prior to eruption, and also in the volcanic eruption that brings these diamonds up to the surface. So in the kimberlite itself, there's a lot of fluid resorption happening. So fluids sort of start to eat away or start to dissolve the diamond along its edges and along its points. And so this process is known as dissolution or resorption. And then you have sort of the original octahedron that progressively gets dissolved away, forming sort of this rounded dodecahedral diamond that we see on the right. And so often that's, more than 45% of the volume gets lost during this process. And so this is actually, a natural process of diamond destruction that is happening all the time. And this sort of diamond resorption or dissolution also forms a lot of surface features on the diamonds that we see. And so trigons, you know, and a lot of other surface features that we see on rough natural diamonds. All of this is a process of dissolution from fluids in the earth and in the kimberlite that are slowly starting to etch away at the diamond, and the diamond slowly loses volume. And so here are some of what those trigons may look like, because you know, not everyone may be familiar with, you know, what rough diamonds look like. We certainly know what polished diamonds look like, you know, but rough diamonds have, you know, a lot of beautiful features, you know, a lot of these trigons, and these trigons are, you know, sort of the prime evidence, you know, that diamonds can be destroyed. They're being dissolved all the time in the earth, in the kimberlite. Some of the other ways that diamonds can be destroyed are natural geological processes that are happening. So if we have heating deep in the earth, so for example, if we have a mantle plume coming in, we know that there's a few localities in the world where we can see lithosphere and diamond destruction. So this is an example. We sort of have a timeline here from 1 billion years ago, and then 1 billion years ago we had the plume and kimberlite eruption. And then after all of this dissipated, all the heat dissipated, so 720 million years ago. And so what happened here during plume eruption was a large portion of the lithosphere and its diamonds were destroyed. So the lithosphere lost all of this. All of this was destroyed by this heating event that happened. And then once that heat had chance to dissipate, the lithosphere was reestablished and a new population of diamonds grew at 720 million years ago. And so this is an example from Canada. So these are the Victor diamonds that formed at 720 million years ago. So this was a new population of diamonds that formed after this massive destruction event happened at 1.1 billion years ago. And then we also have an example of diamonds being graphitized. So this is an example from Morocco, from a peridotite massif. And so this is where we had a portion of the mantle that was actually uplifted out of the diamond stability field. Once again, just, you know, natural processes happening. And then you can see that this is actually a very nice octahedron of graphite. So it's graphite after diamond. And so once again, you know, like this diamond was destroyed just through natural geological processes that are going on. And so we talk about a lot of these things in our column, Diamonds from the Deep, which is in GIA's publication, Gems and Gemology. And so these are some of the titles. Applicable to the talk today is How Old Are Diamonds? Are they forever? And then the follow-up, no, they're not forever. Diamonds get dissolved. And just a picture of us from a conference a number of years ago. And so also we'd like to invite you to email us if you feel you don't know enough about dating diamonds. Feel free to email us. We'd be happy to answer any more of your questions by email. But we also look forward to answering some of the questions in the Q&A, which I think Evan has been moderating for us.
That's perfect. Thank you for that fascinating overview. We are running a little bit short on time right now. It's getting close to the hour, but I will get into a few burning questions that have been repeated a few times here. So the big question that got asked is, do we know anything about the growth rate of diamonds? For instance, if you had multiple inclusions in the same diamond, would they all show the same age? And would they give us any information about how long it takes a diamond to grow?
Yeah, so I'll take that question, Steve, if you'll let me. There are a few examples of where not me, but we, the grand we, meaning all of these people. So I think Suzette actually has an example, and Michael as well up here. They have examples of where they've been able to take inclusions from the center of the diamond and where they've been able to take inclusions from the rim of the diamond, and they've actually had different ages. And there's an example from Russia. There's a Siberian diamond that actually has a billion-year gap between the diamond that grew in the core and the diamond that grew in the rim. We don't know what the growth rate of diamond growth is. We don't know that. We don't have the answer for that. In some cases, all the inclusions in the diamond fall along the same age array. And so we can't distinguish different age populations between the growth zones and the inclusions in the core and the growth zones and the inclusions in the rim. So examples of that are incredibly rare. but they do exist. And when they do exist, they show sort of differences of billions of years. So it is possible that you have, you know, an older generation of diamonds, and then later on you have new diamonds sort of crystallizing sort of around that. But that is not the rule. You know, that is, you know, it depends on every different locality may have a different answer to that question.
Okay, good. Another big question, even bigger than the last question, is about the nature of the sulfide being trapped. Is it molten, and what is the closure temperature? And what are these ages actually telling us in terms of the growth or some kind of prehistory or kimberlite eruption?
Steve can take that one.
It probably is, you know, given the temperature is probably it could be molten, and the closure temperature is extremely low for, it's a good question, a radiogenic isotope system. It's like 400, 450 degrees, something like that. So we don't really worry about that too much in the osmium system, because there's nothing else around that wants to take in the rhenium or the osmium other than the sulfide for the most part. So the sulfides are in silicate rocks, and the partitioning of osmium and rhenium into the silicates is usually so low that the sulfide is the only you know, mineral that these elements want to be in. But you know, we're concerned about it, but surprisingly, even with low closure temperatures, and even you know, diamonds are being held at 1100 degrees or something like that in lithosphere, we get billions of year old ages with no problem. So that's the answer.
Okay, good. Another question here. Someone would like to know, what is the connection between major tectonic events or things happening in a big global scale? Is there a relationship between those sort of events and diamond growth?
Well, that's Steve's favorite topic, so I'll let him answer that.
Well, I mean, I think the answer is yes, and like, for example, Tom McCandless a long time ago correlated, and Ted Ringwood and Sue Kesson correlated kimberlite formation with the transport of fluids by slabs, and they were way ahead of their time. I think we didn't have very good age determinations that supported that. But if you think about kind of the events and the age distribution of diamond formation, in South Africa, for example, I showed that cross section of continent.
Back to that slide.
Yeah, go back to that slide. If you actually think about what we're seeing here, there are many, many hundreds of ages on the right-hand slide, you know, where the 2.9 ages show up on the left. There are hundreds of diamonds that we looked at over all these mines over the years. This is like 20 years worth of work. And this pattern of age shows up. All of a sudden you see that, you know, everything is 2.9 to the east or to the west of this line. The other thing is that the Kopval craton has been strongly depleted, and which would take sulfur out. And so most of these diamonds that we see that we've analyzed as sulfides in the Kopval craton are eclogitic sulfides. These are sulfides that have lower nickel and have this relationship to a slab. I didn't mention this before, but part of the story of slamming together the two cratons is also re-fertilizing the western side with sulfur, with sulfides that became sulfides that were included in the diamonds themselves. So this is one of the better examples. I think Karen has had some good ones in her master's work at Ellendale, where she was able to show that a middle Proterozoic, 1500 million year type of age, remobilized Archean cratonic material.
Yeah, but interesting, in that case, we couldn't actually relate it to any known tectonic event.
Right.
So we know that the ages were 1.4 billion years, And we know that, the craton itself was much older. And so at the time there was just re-fertilization and reworking, but there's no known tectonic event that we could actually relate it to.
Right.
But there is, like, for example, Victor, the 720 million year age, Sonia Orbach, she's related that to, continental rifting. And so we have this tectonic event. So here we have collision, but in the case of Victor, we have splitting apart. So, two continental blocks sort of split apart. There was rifting happening. And in that case, the reworking, the heating, and re-fertilization with fluids formed the diamonds at Victor 720 million years ago. So it's not only collision, but also continental rifting that can remobilize fluids and lead to diamond formation.
Let me say one other thing. That's a very good point. When we look on the continents and try to relate diamond formation to continental geology, it's fossil evidence. Okay, we don't really always know which way the subduction zone dipped or whether the tectonic setting is really what the crustal rocks show that it is. So it's kind of unraveling the geology in a sort of a fossil preserved way. The super deep diamonds of the kind that Evan has worked on a lot, Evan and I have worked on a lot, are these ones that look like they're related to mantle convection today in some ways. And so the hope will be, if we get some ages on these might directly relate to the kind of current mantle convection patterns that would allow us to understand how they relate to the, to the big scale geodynamics, as the questioner asked.
Yeah, and so I think that's certainly sort of like the next target is we have a lot of ages for lithospheric diamonds, but trying to understand the ages. So just to show on this diagram again, we have a lot of ages for these lithospheric diamonds, but it would be great if we could get some ages for these diamonds from the transition zone and lower mantle, some of the diamonds that Evan has been working on. If we can, get some ages from that, that would really inform us about deeper earth processes than we've been able to date so far.
Yeah, absolutely. Now, for the sake of sticking to schedule, we'll take just one more question, which is sort of a follow-up question. Given all of those things that we know about diamond ages to date, do we expect that diamond formation is something that maybe is happening today?
You want to take that? I think, yeah, certainly there's no reason why diamonds aren't forming right now. We just don't have the evidence for it because we can't go down there and see what's going on. But certainly there's subduction happening right now on Earth. The Marianas Trench in the West Pacific, Cascadia, East Pacific, West Coast of the US. There's subduction happening right now that potentially is remobilizing and refertilizing the lithosphere. And so I don't think there's any reason for us to think that diamonds aren't forming right now. We just have to wait for a kimberlite to bring it up to the surface for us.
Right.
I don't want to be around for that eruption, but I want to see the diamonds when they come up.
I mean, it's important to remember that anytime you can sequester enough carbon so that it's not combined with something else like oxygen, and you're deep enough in the mantle, you're going to form a diamond. So there's absolutely no reason why deep slab subduction couldn't produce diamonds today. The problem and the reason we don't see much of this is, as Karen said, we don't have kimberlite eruptions in the oceans, and we haven't seen any kimberlite eruptions ever. And so most magnetism that would bring the diamonds up or plume up rise in mantle convection will oxidize the diamonds, recombine that carbon with oxygen on the way to the surface. And so we could have diamonds down there forming right now that become CO2 in magmas that appear in ocean islands and in arc basalts. And so I've told students when we talked about this, every CO2 content that you measure in a basalt could have been a diamond at depth. We have no idea about that.
That's pretty crazy to think about.
It is.
Yeah. Okay, if you have any further questions, please do find us on Instagram, Facebook, LinkedIn, and Twitter, or as Karen and Steve suggested, email them directly. And join us again next week, where we're going to talk about putting everything under the microscope in the micro world of gemstones. Many thanks to you, Dr. Karen Smit and Dr. Stephen Shirey, for this excellent discussion. Thank you all out there listening for coming and joining us today.
Yeah, thank you very much, everyone. We appreciate your time, and we hope to hear from you. We're happy to answer any more questions.
Thanks, Evan. You did a great job, and goodbye.